So in this video, we're going to talk about the addition of axial stress to our to determine our total tangential stress, to determine our net tangential stress. So we want to know what is our tangential stress at 2 points, point C and point D. So point C is at our inner radius and point D is at our outer radius. Right? So earlier in the lecture, we defined the radius to our centroid. So the distance from the center of our radius of curvature to the centroid of our section cut AA, and we defined using statics. We defined the bending moment at our cross section and uh, the reaction force at our cross section. Okay. All right. So we know that we can use the following equation to calculate our stress due to bending. All right, so the only thing that we don't know in these equations above here is we don't know, so far, we don't know what Rn is equal to. We don't know what our eccentricity is equal to. And we don't know what our y is equal to. Okay, so we need to calculate these three things. Once we calculate these three things, we just need to plug them into the equation. All right, so first things first, we need to calculate what Rn is equal to. So we know Rn is equal to the area divided by the integral of dA over r. Okay, so earlier in the problem, we had, or I should say, we know that the area from the problem statement is given to us actually as being equal to 0.5625 inches squared. So we can just plug that in. All right, and then the integral in the denominator, we need to go back to our tables. Okay, so if we go back to our table a few pages ago, all right, this is our cross section here. So we can use this equation here to calculate um, our integral of dA over r. Okay, so this is table 5.61. So if we do that, we can plug in all of our values here. So our inner BI from our earlier statement was equal to 1 inch. The natural log of um, of Ri divided by Hi. All right, so Ri was equal to 4 inches. All right, Hi was equal to a quarter inch. So we have to add that, not multiply it. All right, and then we have to divide by our inner radius, so that would be equal to 4 inches. And then the second part of our problem is we need to use uh, the thickness of a second part of our section, which would be equal to a quarter inch. And multiply that by the natural log of our outer radius, which was equal to 4 plus 1.5 inches, or 5.5 inches. All right, and then we divide that by um, um, the inner radius plus hi. So our inner radius was 4 inches, and our outer radius was a quarter inch. Or sorry, hi is a quarter inch. Okay, so if you multiply that, so if we take this value, let me call this b here, all right, and we bring that over to our example problem, all right, and we take that integral b, we divide that all through. What we end up getting is we get our value of Rn is going to be equal to 4.49706 inches. Okay, so we can then calculate our eccentricity value E is going to be equal to Rc minus Rn. All right, so if we do that, we'd end up getting 0.4661 inches. Okay, So, um, so then the last thing we can calculate here is we can calculate what our y is equal to. So y again is just equal to Rn minus r. So at when r is equal to the inner radius, y is going to be equal to Rn, which is 4.49706 minus the inner radius is just equal to 4 inches, so we end up getting 0.497 inches for y. And then for r is equal to r outer, y is going to just be equal to minus 1.003 inches. Alright, so RO in this case, so those are our two values for y. Alright, so if we plug those terms into our equation here, I guess it should go the other way. So if we plug our values in here for our inner radius and our outer radius, if we go to the next page here, alright, so at the inner radius, we would get our equation would be equal to negative times the moment. So our moment was equal to 5.54 times 10 to the minus 10 to the third pound inches times 0.497 inches. So that's our y term divided by our area term, so which is equal to 0.5625 inches squared times our eccentricity, which was equal to 0.0446 inches times 4.497 inches minus 0.497 inches. All right, we will get our overall stress equal to 27.45 KSI. We can repeat the same process for the outer radius. All we're changing here is the value of y in this equation. So if we do that, we would get negative 40.29 KSI. All right. So these are the stresses due to bending. We need to account for the axial stress in this section. So the axial stress is just equal to our reaction force divided by our area, cross-sectional area. So we just have 1,000 pounds. It was in tension, so it should be positive. And then our area was equal to 0.5625 inches squared. Okay, so that should give us a stress of 1.78 kpsi. Okay, so we can now calculate the net stress at the inner and the outer radius. So we just have to add in the radius of the inside plus the axial stress. Alright, and then if we do that for the outside too, we just need to add the stress of the outside plus the axial stress. Alright, and then we're going to get 29. So we would get 29.23 kpsi at the inner radius, and then we get a minus 38.51 kpsi at the outer radius. Alright, so that's how you can calculate the stresses within a curved beam that's under a combined axial and bending load.